Good morning. Today is February 18, Tuesday, 11:10 a.m. This is CS 797K, Advanced Data Storage, Lecture 8 on triple parity and beyond. So in this lecture, we're going to discuss about triple parity. So till now, we have discussed about two parities and how to calculate that and everything. So in this lecture, we'll see about triple parity. We'll basically call it PQR. In the last lectures, we discussed about RAID DP, diagonal parity, RDP, and in this lecture, we're going to discuss about PQR. Okay? So if you have any questions at any point of time, just unmute yourself and ask because I'm not checking the chat box. Okay, so this is the course outline. So this is where we are. We are still discussing about block-based protection, basic RAID and complex solvent coding, diagonal parities, RAID. So we are still at the start. We are yet to discuss about data management, moving, and other topics. So the good news is we got permission from Dakota State University of South Dakota to use the Linux boxes virtually to finish our project, um, to build our project in their system. So we will update you after the midterm. So I guess you are aware of the midterm dates. So midterm will be next week on Wednesdays and Thursday classes. So we have two midterms. So first midterm is gonna happen next week, which I'm going to post an announcement. So the midterm topics will be the topics covered before the classes. We are also going to show you the previous midterm questions as well in the next lectures, so that you will have an idea on how on what the things asking on midterms. So yep. So this is where we are. We are at block-based protection. This is RAID triple parity we're discussing about. So this is the triple parity, RAID 7.3. Let me try to open this paper and show you. Looks. Yep. So this is the RAID triple parity and beyond. So if you are interested, you can go through this paper to understand the basic concepts, PDF, and the mathematical stuff, how are they looking like? So what's basically RAID and what's triple parity? How is it performing? And everything you need to know about RAID 7, right? Yeah. So this was implemented by Sun Microsystems in their ZFS in 2005 in their file systems. This is the source code we got. You can go there if you want. I can open the GitHub link and you can go through the source code link, the open ZFS ZFS to the public, and you can go through the source code. Having source code is good sometimes because if you do not understand it theoretically, you can see the implementation of it on Python or Java, and you can understand how the things are working internally. So it's always good to have the source code with us. So you can go ahead if you are interested to see the inner calculations and how are they running the code in their file systems. So the software code supports RAID 5, that is 7.1, RAID 6 PQ 7.2. So they are giving the names as 7.1, 2, 3, and so on and so forth, because we already defined RAID 10. So if they are going to name it as RAID 7, RAID 8, RAID 9, then they're obviously coming to RAID 10 again. So they are out of names for the RAID. So from now on, they're doing it like 7.2, 7.3, and so on and so forth. So other companies also make triple parity, for example, Radix, but it's just a marketing junk. So if we are improving our systems using one more parity, triple parity, we should have some improvement in our system. So this is a piece of junk for just marketing purpose. So if we are building a file system, it's not just for the sake of new system, but there should be some improvement in the system, not just like adding stuff. So PQR reads Solomon coding. So uh, triple parity, so and beyond. So we can go on building as many parities as we need. We're going to discuss three parities in this lecture. It's not meant like dedicating the entire column for a parity. You can scatter your parity bits as well in the RAID in a stripe anywhere. So as we discussed in diagonal parities and stuff like that, in diagonal parity, we are not dedicating an entire column to the parity. Instead, we're throwing it in the stripe. And we need to have a documentation for that called metadata explaining the things about how they built. We're going to have metadata for every RAID where we can go in there and look up where the you know parity bits are located in that particular RAID. So yeah, that's how it works. It's not like dedicating an entire column, entire data to a parity bit. So N data drives 3 parity bits. Of course, we have PQR parity bits. So if we have like 7 data drives, it should be 10 in total with 3 parity bits. Yeah, so that's simple. So we'll see the calculation of P, Q, and R. These are simple calculations. Theoretically, it's simple, but increasing in the number of N drives make it more complicated for the computations, for the handheld computations at least. So we need more computational power with the increase in number of N's. So we'll see how to calculate the parities for P, Q, and R. Again, it's a simple XOR thing. So there's nothing more complicated for you to understand. In exams, we don't ask you the computations to remember, but if you have the basic understanding of things, you can very well answer the questions. But you need to have at least the basic stuff remembering, right? So PQ, parity, it's a simple XOR. We're XORing every data bit here, D naught, D1, and Dn minus 1. So anyone online, why are we keeping n minus 1 here instead of n? We have n drives in total, so we're giving n minus 1. It's simple. We don't we need one bit to know, right? So it's n minus 1. If we have n, we are calculating for one of the parity, so the remaining are n minus 1. It's simple. So 2 power 0 always gives 1, so it's a simple XOR. So P parity is a simple XOR of data drives. So Q parity, each drive doubles the previous. So 2 power 0 is 1. For the next drive, we'll multiply it with 2. For the next drive, we'll multiply it with 4 and do the XOR and so on and so forth till n minus 1. So each drive doubles the previous. It's a simple XOR operation, but each drive doubles the previous thing. That's it. And R parity, each drive 4 times the previous. Okay. So it's 2 square, 2 power 4, and so on and so forth. So 1, 2, 2 times 2 power 2 is 4, 2 power 4 is 16, and so on. So 4 times the previous one. So this is how we calculate the R parity. It's a simple XOR operation, but we're doubling and multiplying it with 4 times with the previous drive to get the parities, P, Q, and R. That's it. So N data drives, the 3 parity drives. So it's a simple XOR operation. That's it. So no theoretical limits to the layer of parity. So we can do just a simple XOR calculation to calculate the parity. So there is no theoretical limits, but there are some practical limits though, such as running out of letters. PQR, then STU, and then we'll go on and we'll run out of the letters to the parity bits. That's it. So also the math gets complicated with each layer, as we discussed earlier. Then increase in number of data drives will also get to increase in the complexity. So NetApp rate triple parity RTP. So you know how we build the RTP. We have 3 parity bits, and we know how to calculate the each parity bit. And again, it's not necessary to have the entire parity in one block of uh, drive. We can spread it, or we can do it like diagonal, anti-diagonal stripes or anything. So we'll see how the NetApp rate triple parity is. So already covered in the previous lectures, and data drives, one RAID 4. This is all we discussed. So one diagonal parity, and it has one anti-diagonal parity. So parity is rotated regularly among drives to avoid hotspots, right? So it uses missing diagonals and anti-diagonal stripes. So as we discussed earlier, if we have diagonal stripes, sometimes we need to extend the row to make another to make fit the another diagonal stripe, but um, so values that read on diagonal parity could be calculated using XOR thing. So NetApp used missing diagonal stripes. I mean, fake missing diagonal stripes to make it. So it's not actually really fake drives or really fake data, but you will see now. So this is the publications of RAID triple parity. This is the paper by Goel. Let me try to open one of the link. Both are same links, but that's the direct link to paper. I guess here we have .pdf paper. So here you can see the RAID triple parity paper by the NetApp people. This is the introduction, diagonal parities and anti-diagonal parity sets, and so on. You can see the calculations here, notations and everything. So you can go through this paper. So I never went over there and read any papers and raids for myself, but I just want to read all the papers available for me during this summer. If I have the chance to teach this class again, I'll have better understanding by reading all of this. But if you are really interested in the work of raids, and if you really want to get to know about raids, you can, if you want to work on raid, if you want to find a job in NetApp in Wichita or anywhere, you can just go there and read all the papers about raid, and you could apply for the jobs. You'll have better understanding on what they're actually working. So fake data, it's not really fake. As I said, it's not really fake. This is the placeholders for data assumed to be zeros. Okay. So RAID RTP uses a zero filled fake horizontal stripe after each diagonal extent to simplify calculations during rebuilding. Okay. So they'll use these fake diagonal stripes for the easy rebuilding thing. Okay, simple calculations. RAID DP also needs fake data, right? So as we discussed in previous classes, if we need one more diagonal stripe, we need to extend our RAID. So we'll use the fake data instead. So R4 discussed earlier needs a prime number of drives to make it a compact or to make it a more clear drive. But if we extend, what happens? We need extra drives in the bottom. So instead of doing that, we'll use the fake data. The diagonal stripes will be disjoint. Okay, so thin provisioned volumes. So for now, class, do you have any questions on how RAID TP calculations work, PQR RAIDs, and the product the NetApp is using on RAID triple parity, diagonal and anti-diagonal stripes and stuff like that? Do you have any questions on that? If you have, you can just unmute yourself and interrupt me at any point of time. Okay.
So I did have one thing to mention though. You reminded me that I did have a Word document about
Yeah.
showing what happens if you don't use the fake data drive with the RAID DP. I will post that on Blackboard
Yes. Okay.
so people can find that. Yeah.
Yeah, we'll post it under the content so you can see when you're looking for
Yeah.
at the PPT. Yeah.
Yes.
In provisioned volumes, most disk volumes are only partially full. Yes. So by virtualizing storage, presenting a pseudo disk with variable capacity, we can more efficiently use the physical storage. Yes. So one of these example is cloud storage. So volumes are only partially full. That means for the cloud storage, they'll provide the service as we go. So if we try to store more data, they're going to charge it. If we are not, they're not going to charge it. So that's the cloud storage is all about here. To the user, it looks like an infinitely expandable volume, but it's actually not. They need to store data somehow. It's not like a real cloud, right? I mean, it's not like raining and clouding. It's the cloud we are using, but they are somewhere storing the data. So it seems like infinitely expandable volume for us because we can store as much as data we need in this cloud, but they will actually store it with prices increasing as more data is added, right? To the vendor, it might be just another file on their network. It might be duplicated to different data centers. So if you have took any classes on AWS, So the Amazon Web Services, they really explain us about this stuff, how they have multiple data centers, and what if one data center loses data, they can just give access to another data center where this was duplicated to that center, and we can easily get access from that center. Or if they have more traffic on one of the data centers, they will just throw the traffic onto another one. Or we can store our data on multiple locations as we wish. We can hard code that thing in AWS as well. So if you have took those classes, you are well aware of what I'm talking right now. It might be duplicated for RAID, for example, RAID 1. It might be virtualized to multiple data servers as RAID 10, RAID 0. So that's why we are discussing about RAIDs. So it's cloud. We are storing it cloud, but how are they managing that? It's again RAID. You need to know something about RAID, right? So metadata, the key to thin provisioning, as I discussed earlier, there should be a metadata file that we need to understand how the RAID was created, or at least how the parities was distributed in the RAID. So not everyone is designing the same RAID, right? Not everyone has the same rules, set of rules. They have different algorithms. So looking into the algorithms gives us an idea of how the data was distributed in a RAID, but having metadata is an add-on, right? I no need to familiarize with any code to understand how the data distributed in the RAIDs. We should have some metadata file. So standard RAID level allocated data algorithmically. So this is how. And RAID 5, 4 plus 1 volume blocks of 0 to 4K plus 4K minus 1 on drives 0 to 3. So here RAID 4. So each point explains about each column. So blocks 0 to 1, 0 to 3 on drive 0, drive 1 on 3, and drive n. Um, this is parity bit. How is it calculated? We XOR things. So this is all about this thing. Just so what we discussed earlier. So this is RAID 4 and this is RAID 5. In RAID 4, the entire disk was dedicated to parity. In RAID 5, there is diagonal parity or rotating parity, you can say. So it's up to the manufacturer how this thing looks like. But yeah, we should have a metadata file. Dynamic disk pooling. You again have in RAID 6, you have two parity bits that's rotating on each other. BP, BQ, CP, CQ, DP, DQ, EQ, EP. See, so NetApp Wichita product. So this RAID 6 was originated at NetApp E series in Wichita. Under the hood, it's 8 plus 2. It's RAID 6. So dynamic disk pooling. So this RAID was originated from our Wichita at NetApp. The thing you need to know. So DDP, dynamic disk pooling, virtual volume allocated semi-randomly. So here's the question. We can, instead of doing it in 24 drives, we can shrink it to less number of drives. It saves us cost. Why are we doing this? You can see like there are a lot of empty drives here. So why are we doing this thing? Because sometimes this helps us in fast read and write operations as well, right? We have more number of drives, we can write it faster and could read it faster from multiple drives. Okay, so dynamic disk pooling. This again, as we discussed, NTAP E series, Wichita product, NetApp from NetApp, RAID 6, 8 plus 2 under the hood, as we discussed, P parity and Q parity, DDP segment 8 and segment 9, stripe 1, data in 0 to 6 plus 9, and so on and so forth. Metadata holds information on where the data are. Again, that's the same repeated point we discussed. So it explains where the data is in that. For example, orange and DDP segment 0 to 9. Yeah, that's what you can see here, 0 to 9. And again, DDP segment 0 is on disk 1, block 0 to 1M minus 1. So you can just go there and look at the metadata and this diagram and understand how the information was scattered in the entire RAID. Yeah, so that's what the meta holds. So what if one drive failed and reconstruct in DDP? So orange, red, green, yellow, brown. Right? These are like different 1, 2, 3, 4, 5. We'll explore the things and we'll get where it is. So we look at metadata, we know how to do the calculations. We know what if one of the thing is getting what we say, what if one of the thing is failed, we know how to reconstruct it. The thing is we need to find it now. We need to find where it is. So for that we need to use metadata, and we'll see where the data drives are distributed, and we'll exert things accordingly to reconstruct a failed drive. So that's the use of metadata. You can very well go ahead and look at the algorithm to see that, but it's again something complicated. Metadata is something easy to find, right? NetApp, Waffle, not really a RAID level. So instead of RAID, we do have unconventional RAIDs as well. So it's not actually RAID, but yeah, this is what the professor's understanding. Get a job in the right department and at NetApp if you want better knowledge. They'll teach you what is WAFL, right? Anywhere file layout. This was there since 1992. So they will teach you, they will train you properly on WAFL. So large cache memory, knows about different file systems, APIs, ext3, FAT32, NTFS, SDFS plus, etc. Old Windows, new Windows, Mac OS. So it knows about different file systems. So that's really useful. Examines incoming data, passes in nodes, etc. Knows which block constitute a file, maintains internal metadata to show where the file is. Yes, as we discussed, metadata is important, can quickly cache the whole file upon seeing read of first block. Okay, and more. There are many more non-standard RAID volumes like WAFL. Some of them are really, really useful, and some of them are just marketing hypes. So there are useful drives, useful RAIDs where we can go ahead and use that, or we have some of them which are not really, really useful. So they are just for marketing hype to market their products. So this is the final slide for today's lecture. So I think we have discussed it like 25 to 30 minutes. So yes, any questions, people online? So the bottom line is we do have more than two parities, three and beyond. We discussed how to calculate PQR parities. It's simple calculations, but math get complicated with the increase in N drives. And we have discussed about the products by NetApp and the other products which are just marketing apps that are not really useful outside in the real world. And we have discussed about non-conventional RAIDs. We have discussed about the metadata and its uses and how to find it. And if we lost one of the data block that's distributed around many different drive pools, we just need to find the metadata, and we'll just find the data drives that are used to rebuild the data drive. And that's simple. That looks complicated, but that's simple if you know the simple XOR operation and you know how to read the metadata file. So that's what we have discussed in this lecture. If you have any questions, we will try to answer that question, or else we'll try to build a logarithmic file, which is very important in midterm exams. And the previous midterm exams, many people are doing mistakes in building logarithmic tables and answering logarithmic table questions. That is very simple, but most of the people are doing it wrong. So we will discuss how to construct it in the remaining time of this lecture. Okay. So any questions? I'll stop sharing and stop recording. Oh, yeah. Stop recording. Yeah.